All right. So I'm going to make a hopefully brief video on how to combine a single red, a single green, and a single blue frame into a color image. And there are actually a couple ways you can do it. There's level 1, level 2, and level 3. And I'm going to show you those 3 levels and all the buttons and knobs you can turn and push and turn and levers you can pull to manipulate it. Okay. So we provided you with a list of objects and recommended exposure times, and you've already collected these data. So let's go to Afterglow, and you want to load your 3 images in. Probably want to delete everything else first, so you're just working with these 3. And you want to click on each, make sure it's loaded into the browser. So this is our B image. This is the Omega Nebula. This is the red image taken in the R band, and this is the green image taken in the V band. V stands for visual, the middle of the visual spectrum, which is green. So, of course, they're all black and white images, but they're taken at different wavelengths corresponding to blue, red, and green. Okay, so the first thing you want to do is you come over here to the Cosmetic Cleaning tab. And that's because if we zoom in here, you see there are little defects. See these single pixels? We call that a hot pixel. It's just defective. And there's cold pixels too. They're harder to see because they're like pure black. But they're in there as well. And we want to get rid of them. And we've built in a fancy cleaning algorithm. So I'm going to select all of the images here and just leave all the defaults as they are and submit. Now this takes a moment. It takes probably a minute per image, maybe a little bit less. And I think it scales. I think it works if, say, 20 students press this at the same time. It still only takes about a minute per image, I think. I guess we'll find out when you try this in class. If it proves to be a problem, jams everything up, then you can skip this step. This step isn't super important, or you can do it on your own outside of class. I just can't remember if this step scales or not. Let's see, we're at 67%, so it's cleaned 2 of the images. It's working on the final image now. If you're using the Prompt 6 telescope, it also has a bad column that runs completely through the image, and this will clean up most of that bad column. So that's a nice thing as well. You try and make a pretty picture and you don't want to have a streak or a line going straight through it. There we go, 100%. Let it hit complete, and then it should reload the frame, cleaning up defects, removing the bad column from Prompt 6 images, these hot pixels. Other things like cosmic rays strike the detector, and usually that gives you a little streak or a cluster, like that could be a cosmic ray hit. Just waiting for it to complete. It says it's 100% done, but it needs to complete. Okay, it's complete. And look, the image is updated and those bad specs are gone. And again, if you're on Prompt 6, most of that bad column's gone. And there's a little patch where the bad column gets kind of thick, and the current algorithm doesn't remove it completely, but it will improve your image dramatically. Okay, that's step 1. Step 2 is we have to align. So after cosmetic correction or cosmetic cleaning, come down here to the aligner, and first make sure you have a WCS, a world coordinate system. So if you move your cursor around down here where it says right ascension declination, there should be actual numbers in there. It shouldn't just say zeros. you don't have a WCS, probably your image wasn't deep enough to have enough stars in it. So maybe you're shooting clouds or thin clouds, and probably your image is such crap anyway. It's not worth proceeding. Go reshoot your target, get new observations that have enough stars. And if you have enough stars, Skynet automatically gives it coordinates. And we can use those coordinates to align the images. So now I'm going to select all three of these images. That's why I said clear out everything else beforehand, so we can just then select all. Reference image doesn't really matter. I like using the red image as my reference almost always, because it's always the highest quality of the three. You can really see the difference there, but it doesn't really matter. Make sure these are all turned on. Crop, enable rotation, enable scale, enable skew. Mode should be WCS. That can be 100. And I'm going to submit. It's going to align, in this case, the blue and the green one to the red frame. And it should be pretty quick. And it crops them, so they're all exactly the same size. And that's going to be important. When we combine them into a color image, they have to be the same size. So you probably didn't notice much of a change. It's loading in the now cropped image, aligned and cropped, and this one too. Okay, now we can group them. So I'm going to select all three. By pressing that button, I've selected all three. And if I click on the triple dots and hit group selected, now makes a group. So this is called a multi-level, multi-HDU. It's still a FITS file, but has multiple levels to it. So if you click on the group level, what you see is a combination of the three. It's kind of adding them together. And it doesn't look like anything now, but right-click on the blue one, color map it to blue. Right-click on the red one, color map to red. Okay, and right map on the green one, color map to green. Okay. So I said there's levels 1, 2, and 3. This is like level 0. This is our starting point. Okay, and that doesn't look bad, but we're going to try to improve it. So come over here to the top tab, show display, and we're going to select a layer. I like to select the red layer, as I said, so let's select that one. And then under color composite tools, we're going to start, this is level 1, link all layers percentile. So it's going to match the layers up. Okay, let me press it first. Okay. And you may not see any change because I think that's the default, but do it anyway, because then we can edit things. Anyway, let me see if I can explain what's going on here. We're in percentile mode. If you look down here, the background level is 10%, the saturation level is 99%. So for each of these histograms, it's going 10% of the way in and setting that to the 0 level, and 1% of the way from the top. It's off the screen. Oops, don't want that. Reset. 1% of the way from the top and setting that as the brightest for the red, for the green, for the blue. So it's the background is different. The position of the background is different for each, and the same for the saturation. It's 10% in, 1% in from the top. And you can change those if you want. Now that they're all linked to the red, like if I go to the blue level here, it says linked to the red. If I go to the green level, it says linked to the red. It doesn't let you change. You see the background and saturation, they're gone. They're all controlled by the red. Now in Opus, you've been using stretch modes like linear, log, square root, hyperbolic, arcsine. But with these color images, we have a fancier one called Midtone. And once you link everything, you can control everything through the layer you link to. And so let's select Midtone. And then you probably want to hit default and see how the quality of the image improved. Let me go back to linear just for a second. And hit default. See how the stars all kind of, you have that big white blur? They're all saturated. In the red, the green, the blue band, going 1% of the way in from the top of the histogram. All these stars are brighter than that. And so you just have these kind of white disks, and it gives your image kind of a cheap look. This is like astrophotography from the 70s or something. But if we go to midtone, and I'll hit default here, see the stars no longer saturate so aggressively. Now you have a background level, you have a saturation level, and you have a new thing in between called midtone. And probably for these images, you can just leave background at 1%, saturation at 99.999, and you can control everything that you want to control through the midtone level. It's something called a control point. If I raise it, like I'll make it 99, that will make everything fainter. The stars still look good. I can go to 99.9. That's too much. 99.5. Anyway, you see the game. Or I can go in the other direction, bring that down to 95, and things get really bright. Or here's 85. Things are starting to get too bright. I'll go back to the default 97.5, and I'll leave it up to you to adjust those. Anyway, this is astrophotography level 1 image using the percentile mode. It's a decent approximation, the percentile mode, but the trained eye will look at this and the colors just won't look quite right, particularly if you look at the stars. Like I see kind of a greenish tint, just a hint of it. Maybe it's because I'm a trained astronomer and I know what stellar colors look like. But stellar colors look like the colors of an incandescent light bulb. A really hot light bulb glows white. Cooler ones are, orange, and really cool ones are reddish. And stellar colors should be on that spectrum. You can buy these, we're all buying the compact fluorescent bulbs now because they're better for the environment and all that. And they try really hard to get them to mimic thermal looking colors, the colors of incandescent bulbs, the colors of stars, but they're never quite right. And so the colors always feel a little bit off with the fluorescence. And in this image here, the colors feel a little bit off. Okay. Now, if you're happy with it, level 1, fine. Download it. Don't do the screen capture. You've done that a lot in Opus, but if you click this button, it exports the whole image, not losing any pixels. And so if you're happy, you can export it and post on social media and say great things about the class. Okay. Level 2. Instead of using percentile, we're going to use the background stars to set the levels of the red, the green, the blue. All these stars are cataloged. We know how bright they are in red, green, and blue. And so built into Afterglow, we have tools to match it up, and we can use that to set the levels. Then the stellar colors will look like they should. So level 2, let's come back up here and make sure I'm going to reference to the red still, but instead of link all layers percentile, I'm going to link all layers pixel value. Now, initially it does, it's goofy. You see the red histogram, how it's farther to the right than the green, and the green's further to the right than the blue. It just means I got more counts in my red image than in my green, and more counts in my green image than my blue. Maybe my exposure time was longer in the red, or the telescope's efficiency of bringing in red light was higher. The color's meaningless at the moment. We haven't calibrated yet, but we've linked the pixel values. We're no longer linking percentiles, but pixel values. Okay. So to calibrate to the stars, we're going to go here to photometric calibration. And I'm going to select my red image, my green image, and my blue image. It normally loads those up all by itself. It can figure out which is the red, the green, the blue. But I was doing something before I shot this video and it's probably confused. And so it's making me set them. Fine. And measure 0 points with field calibration. So let me just cancel out of this for a second. under settings, hopefully you haven't messed with this. I did mess with this. I'm glad I checked. Your defaults probably look like this: constant aperture, and you can actually press that button, restore aperture default settings, and source extraction, restore default settings. You want to use the defaults. You probably haven't ever changed these throughout Opus, but if you did, you probably want to set them back before we do this. Okay. So color calibration, I'm selecting the red, V is green, B is blue, and I'm going to press that button, measure 0 points with field calibration. So what it's doing now is it's extracting all the stars in the image, comparing them to catalog values, figuring out what factor it needs to multiply the image by to get to the catalog level. It's almost done. It's done. And so the number's updated. Reference layer can be anything. I'll just pick the red. White balance. This is kind of a subtle thing about how the eye works. You may think if you have the same amount of red, green, and blue, it'd be white. But the human eye actually sees that not white. If you have a thermal spectrum peaking in the blue, that's what the human eye sees as white. So this is an adjustment for, changing it such that matches exactly what the human eye would. It should default to black body peaking in B filter. Just leave it there. And extinction, this is dust. Dust along the line of sight reddens your image. And that's level 3. Right now, leave that at 0. I'm going to calibrate. Okay, you can see the colors adjusted. So this is what it looks like to the human eye, essentially. If you look through a powerful enough telescope that you're bringing in enough light that you can see the colors, they look like this. And so these are pretty natural looking colors, albeit a little red. And they look a little redder than they probably should because of dust along the line of sight. Okay. But maybe you want to quit there. These are the colors that you will see looking through a telescope. Again, you can play with the mid-tone level and adjust that if you want to, and then download. Now, level 3 is correcting for the dust. Dust blocks light, and it blocks blue light preferentially. Blue light scatters more easily, and it's why our sky is blue. The blue light from the sun scatters all over the place, painting the sky blue. So dust between us and the Omega Nebula, has made everything redder than it should, because all the blue is scattered out, absorbed, and just the redder light has an easier time making it through. And so we can correct for that. Now, in the table, there's some recommended values, and May looked these up, and some of them should work perfectly. But some regions are kind of complicated. They may have variable amounts of dust at different parts in the image, and particularly star-forming regions, these H2 regions. Like when May looked up the Omega Nebula, it said 1.5, and I tried it, and it's way too much dust correction. So we scaled it down to 0.75. But really, this is just a recommended starting point. We're going to let you play with this parameter until you get something that feels right. So to correct for dust, you go back to photometric calibration under EB minus V. Here, I'll put in the 1.5 initially so you can see the effect of too much dust correction. So, boom. Okay, it took out, the dust is taking out the blue. This puts the blue back in, but that's a little too much, I think. Again, I'm used to stellar distributions, and that's way too many blue stars. So I'm going to back it down a little bit. Try 0.75. Yeah, that looks okay. Pretty good, actually. Nebulae tend to be red. The hydrogen in the nebula emits the Balmer sequence, which is, well, it's kind of pink. If you put the 4 visible light bomber lines together, it's kind of pink, like you have out here. And oxygen also emits oxygen, twice ionized oxygen is also a big emitter in nebular regions and emits kind of a greenish blue, which combined with the bomber pink gives you whitish zones. And so the pink area out here is hydrogen, the white area is hydrogen and oxygen. And really red areas, that's sulfur, but that's usually faint, once ionized sulfur. So that looks pretty good. Again, you can play with the midtone level, you can play with the extinction, but that's our level 3 image. So you can download it here. And then using external software if you want to crop it or whatever, but post it on social media and say great things about your astronomy lab and your astronomy instructor and your TAs, of course. And I hope you had a good semester. Okay, I'm going to stop.